So this one will be a little bit of a break. All right, so we have AB is equal to AC. And see how fast we can solve this. O is the circumcenter. M is the midpoint of BC, and BH is an altitude. All right. So here's the midpoint M and the altitude BH. And X lies on this so that AX is perpendicular to AB. Okay. So we have, this is H, and this is X. And prove that MH bisects OX. I bet you guys have already solved it. Let's see. So let's see, can we use projective geometry? I'll make it something like that. Obviously, AO and M are collinear. It looks like it's just some sort of projective geometry. So H, so yeah, can we use poles and polars? Like if we draw, yeah, I guess we could either draw the circle diameter AB or let's see, maybe it's worth drawing MH, and then we could see where it intersects OX. We want to show that's the midpoint. And then can we project through H onto BC? We can try, but draw this parallel. I don't know if that does too much. So yeah, maybe there's a better way. Can we use similar triangles? So we want to show D is the midpoint of OX. Let's see. It is, so I drew the diagram, right? Let me draw this. You know that E is the antipode. Is there any other midpoint we could try to use? So we could take the midpoint of AX and we could try to show that so obviously F is the circumcenter of AF. Yeah. We could try showing FD is parallel to AM, which is the same as saying that FD is perpendicular to BC. I don't know how helpful this is, but this is harder than I would think. Let's see. I'm going to make it look a little more because OX almost looks like it's parallel to BC, which isn't true. So I make this like a flatter triangle. Yeah, then it's doesn't look like it as much.
I think I've solved it.
Okay.
So can you let K be the orthocenter of ABC?
Okay. Well, yeah, it's just this point. Yeah.
Yeah, exactly. And then can you let AK intersect circumcircle ABC at a point?
Yes.
Let's call that point N.
Okay.
So I'm gonna use Menelaus theorem for triangle OXK and the three collinear points M, H, and D.
Okay.
So we will calculate the ratio dx over do in terms of hk over hx and mk over mo. So
Okay.
in other words, we need to show that hk over hx is equal to mk over mo.
Okay.
Um, can you connect ck? We will have ck is parallel to ax
I think
since they
they
are both.
connect CK.
Yes. And it will be parallel to AX because they are both perpendicular to AB.
Yes.
So HK over HX is HC over HA.
Okay, because these are
Because that
parallel.
just tallies. And then we
Yes.
also have HK is parallel to NC.
Okay.
So HC over HA is equal to KN over KA.
Okay.
Now we know that KA is actually twice of OM, and KN is twice of MK. So we are done.
Ah, all right. I like that. So yeah, I'm thinking instead of Menelaus, is there a way we could like project, like Menelaus isn't bad. Like you want to show K, but I guess we'd have to draw a parallel because like we'd have to draw yeah, okay, Menelaus is fine. So yeah, I'll use that. So by Menelaus, XD over XO times OK over KM. Well, I think you did the, yeah, so MK over MO times OD over DX. We'll just put in parentheses, MK over MO times OD over DX. And I think it's actually MK over MO. Yeah, oh yeah, I did that. Times XH over HK equals 1. And I'll just say that means that dx over OD equal to MK over MO times XH over HK. Oh, whoops. I need to put it on a separate line. And then, so let orthocenter of ABC. So CN is parallel to BX, and both are perpendicular to AK. And then we also have CK is perpendicular to AB. So we have XH over, so first of all, AX is parallel to CK. And that means that XH over HK is equal to AH over HC. And then, which is equal to AK over KN. And that's since BH is parallel to CN. And then AK over KM, or AK over AK is 2OM, and KN, so AK is 2OM, and Kn is 2 Km. So combining the above, dx over Ox equals 1. Dx over OD implies dx equals OD, and that means that MH bisects OX. So yeah, I know I should have probably defined some of the names of the points, like D. I'll just write that. Let MH intersect OX at D. I think it's clear what N is. I'm just lazy. I'm not going to write out the definition of N. All right, thanks for the solution. So I'll move on to another one. See what time it is. 11:13. Let's see how many more we can solve. Sorry. That one's a little tricky. It uses isogonal conjugates. So this one's a middle riddle, although there's kind of a lot of information in it. So let's see what we can do. You want to do another riddle? Okay. Yeah, this middle riddle has a lot of information, but yeah, let's do a riddle. So this one uses isogonal conjugates. This one does not use isogonal conjugates, but it has a good amount of information. So Ravi, do you want to do the isogonal conjugates? Okay, this one's okay. All right. So we have a triangle with circumcenter O, and AX is a diameter. And again, we have symmedians. So it doesn't say symmedian, but the tangents intersect at S. So this is O, AX is the diameter. Let's draw the tangents. Intersect at S. H is the orthocenter of ABC. QH is perpendicular to AO. So let me draw this a little bit different. Yeah, so I'd like, yeah, I think we want QH perpendicular to AO. It's the best way. Maybe something like that. So QH is perpendicular to AO. And J is the midpoint of OQ. Let me close this. J is the midpoint of OQ. And V lies on HX. such that Sj is perpendicular to SD. Interesting. So we drop a perpendicular. So OQ is going to be parallel, it looks like, to SV. And U lies on AO such that SU, okay, so we're going to have to draw AO. Obviously, that passes through X. And we want to draw this. We want it parallel to BC, so this will be U. We want to show the angle bisector of AUV is perpendicular to BC. Okay, so yeah, there's a couple ways to kind of phrase this, but like we want to show angle VUE is AUS. It's another way to say it. Okay. So yeah, a lot of information. I'm going to hide everything and then redraw it all. Where did I even use point X? Oh, because V lies on HX. Okay. So this obviously passes through the midpoint of BC. So yeah, these concur at the midpoint. And these look like that. And this is perpendicular. Okay, that's not that bad of a diagram. It's a little complicated, but not the worst. Oh, we need to draw SV. Okay, it's a little more complicated then. So these are parallel. I wonder if it's a parallelogram. Length QD SV. Nope, it's not a parallelogram. So O is the midpoint of AX, J is the midpoint of OQ, F is the midpoint of BC. We have a lot of midpoints here. And maybe we could use harmonics to help with this problem. Because if we, like, we could form a rectangle, right? So we want to show that this is like a harmonic bundle. I don't know how much we can do with that, but so yeah, I mean, I guess another way to say it is we're going to show like EBIX is harmonic, but I don't know like where we would go from there. So I'm not sure how good of a strategy that is. So QD is, I was going to say, actually, never mind. QJ is perpendicular to AX. No, QD. QD is perpendicular to AX. So yeah, if we drew this point, then H is the orthocenter. I don't know if that really helps though. We find, yeah, so what's our ultimate plan? Do we want to use projective geometry? Do we want to show UVE is similar to another triangle? So yeah, is angle U, let's see. So this angle right here is 90 minus this angle. So that's the same as angle HFO. Sorry. Let me check the chat. V is complicated. Yeah. Because V is defined in terms of J, which is not that obvious. So let's see, this angle is 90 minus this, which is HFB. So we have this. Yeah, I want to find a triangle that's like similar to UVE. That's my goal. So it has like this angle. I want a triangle that has like this angle and this angle in it. See you, Yash. Thanks for joining. So yeah, I want a triangle that has this angle and this angle in it. So yeah, this problem looks so hard. You guys want to keep working on this? It's like scary to me, but I can keep going if you guys want.
Ravi, what do you think? I think we should work on it a little more.
Okay.
Like,
All
I
right.
think we should just start analyzing point Q and point J first.
Okay.
And somehow we can relate it to point V.
Okay. All right.
Like, for instance, we have QDOF is a cyclic. Like, that is kind of
Useful.
easy to see, but
All right. So you guys are a little less scared than I am, right? All right. I'm thinking about projecting onto OS. So X, I, V, E, X goes to O, I goes to the point of infinity, E go, well, yeah. So yeah, I forgot to draw these. But yeah, obviously this is a harmonic bundle, SB, SF, SC, SE. We want to show this as the harmonic bundle. So it almost looks like this, but I don't think it can be true that AU is parallel to BS. Yeah.
The circle with the diameter OQ also passes through the intersection of HX and ABC,
Okay.
and also intersection of AH and
ABC.
ABC. Yeah. So we can define J as the center of a circle passing through LOFMA, maybe. It will be
Okay.
more familiar to us.
Okay, so we can, like originally it was a midpoint of OQ, but we don't really need this. It's the circumcenter of MOL. What is D? Did I define D a certain way, or is it just the intersection? I forgot. Oh, yeah. It's just the foot of the perpendicular, but we don't need it anymore. Okay. Okay. This is be like the midpoint of that arc. So yeah, SV is parallel to OB. I think. No, it's not true. It's perpendicular to SJ. Hmm.
Can you show point Q?
Yes.
So if we can prove that QM is perpendicular to UV, then it is we are done.
Really?
If we
Okay.
can prove that the QM is perpendicular to UV, then we are done.
Okay.
Because we can use orthogonal harmonic bundles. Like we need UX, UV, UI, US. That cross ratio is -1. And then if we just we have QH is perpendicular to UX, QC is perpendicular to UI,
Okay.
and Q and the line through QN perpendicular to BC is it is perpendicular to US. So if we can prove that UM is perpendicular to UV, then we can use harmonics.
Okay. I like that. So yeah, we want to show that these are perpendicular. That's a really good idea.
Which is the same as saying OM is parallel to UV.
Okay. Yeah, that is like, I got to use that trick more. Okay, so yeah, we want to show this UV, UI, UX, US is harmonic, and if we could show that QN is perpendicular to UV, then we also know already that yeah, let me draw. So yeah, we know that QG is perpendicular to UG. We know that QD is perpendicular to AUA. That. Okay, so this one, for this line we have D. For this line we have F. For this line we have M. So D, F, M. And so is it because, like, what do we know is harmonic here? Is it is like D?
It is HM, QH, QM, QB, and infinity point.
Okay, that makes sense. I wonder if do we even need harmonics for that, or is that just like an angle chase? Because like,
yeah, we can just use angle between the perpendicular lines.
Yeah, but still, it's a interesting idea. And QM is tangent. Is QM tangent to the circle? Is that obvious? It's ABC. Yeah, it's, I think
Yeah.
it's obvious, right? Because it's a right angle. Yeah. Okay. So yeah, it's kind of like the same as showing that this is cyclic. Does that pass through D? Yes. Okay, so now yeah, maybe that would help. Let's see. So SV is perpendicular to SJ. And I could try drawing this. And then we want to show PV bisects IPE. Though I don't think that does much. Okay. Yeah, UV is defined in a tricky way. So what if we project through U onto this circle? Yeah, I like that actually. So V goes to N, I goes to G, X goes to D. So we have NGD. Yeah, basically we want to show we have a harmonic quadrilateral. Okay. And this just goes to the reflection of U over S. So we want to show that we have a harmonic quadrilateral. We want to show that N, I don't know if this really makes it that much easier, but so this is a rectangle. We want to show that N NP, NPG, NPDG is harmonic. And this, yeah, I like this idea because, oh, I thought this was a rectangle. What am I missing here? This is not a rectangle. Yeah, it just looked like one. Or wait, maybe it is. Yeah, that's a rectangle. It's just this is not the bisector. F is not the midpoint of this side. Yeah. Okay. So let me draw that. G, D, P. We want to show that that is harmonic. But wait, G is like the antipode of P because it's a rectangle. So yeah, we just want to show GB equals GN. Or PD equals PN. Which is the same as showing that this, well, but we know this is an angle bisector. So wait, maybe I'm going in circles here. Yeah, I think I went in circles, but because yeah, if we show that this is perpendicular, then it, yeah, does exactly what you said. So yeah, I just wanted a circle. Although I don't know, well, yeah, because I have to use somewhere. Like maybe I could define it.
I think I have an idea that is very close to the solution.
Okay.
Like really close. Like I just transform them to like familiar points of triangle ABC. So yeah, it shouldn't be too hard.
Okay.
Can you just hide the big circle because I was going to um like my ID doesn't use it.
Okay. Yeah, I'm gonna delete all the stuff I added. Your idea doesn't use point G, right?
Yeah.
Okay.
Yeah, just can you delete point E also
Yeah.
and K too?
All right. I'm gonna add back in this segment.
So I'm gonna tell my idea. So can you draw a circle with center S and radius SB?
Okay. Center S and radius SB.
I drew the circle because I want to find a line perpendicular to SJ so that we can use the fact that SV is perpendicular to SJ.
Okay.
So can you can you call the intersection of XL and OM?
XL and OM. So right here.
Yeah, and also LM and BC.
Okay. LM and BC.
I don't think it is collinear with J because
Okay.
it would be too,
Yeah, no, you're right. You're right.
yeah.
LM and BC.
So maybe if we can just calculate the powers and stuff, we will prove that EF is the radical axis of circle with center S and the circle OMQ.
Okay. So EF would be the radical axis of these two.
Yeah, I haven't proved it yet, but like E and F are not really, they are familiar point
Yeah.
because L, M, X are familiar. So hopefully we can do this like little problem.
Yeah.
So can you connect EF?
Okay. So those are the radical axes. Let me draw the other intersection point. All right.
I think you shouldn't draw that because it will be, very complicated, but oh, it's okay. As long as we can still look at the points, then I think it's okay.
Okay.
Can you let the OM intersect BC at a point?
Okay.
So we can easily show that LBMC is a harmonic quadrilateral, so LMS is collinear.
Okay.
Okay, so let me see. So we have proven that EF is the radical axis. So EF must be parallel to SV.
Okay. Because
Can you
because
connect
SV
EF?
is perpendicular to SJ. Yeah, that makes sense.
Yeah.
Sorry. Sorry, I'm going to move it back. It looks like these concur, so I was trying to make it so it doesn't look like that.
Can you connect EF?
Oh, yeah. Sorry.
So I'm gonna prove that triangle PEF and triangle UVS they are homothetic with
Okay.
center L.
Okay.
Because if we can do that, then we will have UV is perpendicular to OM, parallel to OM, which is what I stated at first.
Yeah.
So we know that uh, EF is parallel to SV.
Mm-hmm.
So we have also we can see that I think that also the quadrilateral HEPF and XVUS are homothetic too. Like if we
Okay.
can prove this, then we can just show that UV is parallel to OM.
Okay. All right. Yes. So that looks really close. I'm going to write the main ideas out for the people on YouTube. So we want to show that E and F lie on the radical axis of the circle BIC, or yeah, what circle was that? BGC. Oh, the circle with center S passing through B and C. So let omega be the circle through centered at S through E and C. Prove that E and F are on the radical axis of omega and LDOKM. Okay, so if we write out the steps, first show that LDOKM is cyclic. And then, okay, thanks for typing it up. All right. So EF is parallel to SV, and that ultimately shows that since QMP is 90, then we have QHP is 90. So HP is parallel to XU.
There is actually a tool on GeoGebra that you can highlight the quadrilateral, like
Okay.
yeah, that one. Can you just highlight HEPF and
Okay. So HEPF
EPF and go back to H, yeah, and also XVUS.
XVUS. So
Yeah.
we could show a homophily at L takes those one to the other.
Yes.
Takes HFPE to XSUV. Even doing it on GeoGebra is still pretty awesome. Yeah. And so once we know that, then we can use the two harmonic bundles, or well, okay. Then since the theorem is true with this, then it's also true with this, because yeah. So I'll just say the angle bisector of HPE is perpendicular to BC, which solves the problem. All right, this was pretty awesome that we were able to finish this, and that I was about to give up on you guys, and then you guys decided to continue with this problem and you figured it out. So that is so awesome. So thanks a lot for the solution. Okay, so Khan just wrote up a little bit more, so I'll just type it out in the corner right here. But yeah, thanks for sticking all the way to the end like this. So yeah, we still have to show E and F are on the radical axis, but that probably isn't very hard. All right, so I'm gonna end it here since we're a little over time. For all of you watching on YouTube, thanks for watching. And I want to thank all the different participants that participate on the session. So if you want to join me in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of the video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again for watching and have a great day.